Thank you very much. Right, okay, so first of all, I must say that, Fritz made very nice introduction, and he already told at least what I have in the first few slides. Second disclaimer is that, of course, as you know, it was last-minute substitution, so I didn't have much time to prepare slides, so if there are any misprints in the slides, please forgive me. And another disclaimer is that, of course, in this program we have, as been advertised in the description, we have three different groups of people, so periodic, almost periodic, and random, but this is not the only division between people here. So I think much more important division is between two groups, discrete Schrödinger and continuous Schrödinger groups, right? And what I will be talking about today will probably make no sense for discrete gang because it's high energy asymptotic, so which does not exist in discrete Schrödinger, so I should apologize about this. Right. So as Fritz has explained to us, though for people who study continuous Schrödinger operators, high energy asymptotics are quite important, and he gave a list of people who were studying them. And one thing you could study, of course, many people studied the asymptotic behavior of the counting function of eigenvalues, but also very important object people studied was the what I will be calling the local density of states of the spectral function on the diagonal, so the kernel of spectral projection on the diagonal. And anybody who had a brief look at the results knows that when we try to obtain as good asymptotics as possible, our main enemy is the loops. So if we talk about, let's say, asymptotics of eigenvalues of Laplace or smaller order perturbation of Laplace operators, so loops are, you start at point x, you go in start geodesics from point S, and as soon as the geodesic ends at some moment of time, again at point x, this is a loop. And the more loops we have starting from point x, the less regular asymptotics we have. So loops are our enemies. And therefore it is natural, if we want to obtain very regular asymptotic, to study a situation when we have no loops at all. So for example, RD. So this is what I will be doing. I will be, my unperturbed operator will be Laplace in RD. So of course, all geodesics in RD are straight lines, so there are no loops. Right, and potentials that to begin with I will be considering, I have called them USB, and the copyright for the name belongs to Sasha Sobolev, so they stand for uniformly smooth bounded, and this is just the fancy way of saying that this is potential that are bounded, and all their derivatives are also bounded. Right, I don't think this class has any special name, so this is what I will be calling it. And I will be considering Schrödinger operators with potential from this class. And notation is the same as in Fritz's talk. So by E, I will denote the spectral. I will denote the spectral projection. By capital E, by small e, I will denote its integral kernel. And by capital N, I will denote, which depends only on one special variable, I will denote the projection of the restriction of kernel of spectral projection on the diagonal. And many people call this function N the local density of states. Now, this function has the advantage of existing in this generality. So for all potential from this class, the local density of states is something well defined, as opposed to, of course, integrated density of states for which we need to impose some extra conditions on the potential. And Well, I mean, there is a theory that the older a mathematician becomes, the more he or she is inclined to formulate conjectures rather than prove theorems. So I'm moving in this direction. I'm not quite there yet, so I will start by formulating conjectures, but there will be some theorems. Right, and okay, to show you that I am even have started my direction, I will formulate two conjectures, not one. Right, and those are conjectures that Fritz has mentioned in his talk. So first conjecture is that the local density of states has complete asymptotic expansion for large energies, lambda going to infinity, which, what do I mean by this? It means that as soon as you truncate your infinite sum at some point L, then there will be finite asymptotic expansion where remainder is O capital O small or whatever it should be. Now, this conjecture probably for many people studying spectral asymptotics seems to be really too good to be true. So I will formulate another conjecture that looks a little bit more plausible, but in fact these two conjectures are equivalent. Well, before formulating actually second conjecture, I will tell you what is known about coefficients. So the good news is that what is required of us is just to prove that such asymptotic expansion exists. Coefficients have already been computed by, again, Fritz has already mentioned, by people studying heat asymptotics of heat kernels. So Poltorovich, Hitrik, Poltorovich, Karateyev-Pushnitsky. I think the main contribution here was by Poltorovich, and just in case, Poltorovich is Iosif Poltorovich, not Leonid Poltorovich. Right, so in particular, there are these formulae for first two coefficients, A1, A2, and if you look carefully at formula for A2, you will see that there is term d minus 2 in numerator, so which means that this term vanishes when dimension is 2. And in general, if dimension is even, then actually many terms turn out to be 0. So sometimes this full complete asymptotic expansion actually means that there are finitely many terms plus O capital of lambda to minus infinity. Right, so second conjecture that is in fact equivalent to the first one is, suppose you have two potentials from our USB class, and suppose that we know that the potentials are the same, identically equal in neighborhood of some point x, then the difference is difference of corresponding local densities of states is decays faster than lambda to any power. So essentially, if you keep potential the same in neighborhood of point and change this potential somewhere far away, then the change in local density of states is not going to be big. Now, I must say that how did I actually arrive at this conjecture? So we have proved the results. So later on, I mean, Fritz has already announced, I will tell you the theorem. The main result will be that these conjectures hold for periodic and quasi-periodic, almost periodic potentials. But once we have proved it, I thought about the question, I mean, to which extent this complete asymptotic expansion is actually universal. I mean, is it complete asymptotic expansion, is it there just because we have some structure at infinity, or maybe it's more general phenomenon? And my first impression was that, I mean, it could not possibly be the case that for all potentials from this USB class we have complete asymptotic expansion. Life, I mean, it is probably too good to be true. So give me 10 minutes, I will construct counterexample. Well, after a couple of hours, I thought that, okay, well, maybe it was a bit too optimistic, so give me maybe a couple of days. Then after a couple of days, I managed to construct some examples, and actually we with Alex constructed some nice examples that were, I mean, they were nice counterexamples if some object does not go to 0 for large energies superpolynomially. And then after a while, when you think a bit more about this, you realize that in all examples you construct, these objects actually do go to 0 super polynomially. So, and then after a while I thought, okay, maybe the problem is not, it's better not try to construct counterexamples, but to actually prove this conjecture in this generality. But before doing this, I have asked several people who are experts in spectral asymptotics. So, and actually the opinions were divided. So Ivry told me that he believes the conjecture is obviously true, but he hasn't got the faintest idea how to prove it. Melrose told me he did not really, didn't have any firm opinion about whether it's true or false, but if he had to put money onto something, he probably would put money to it being false. Barry Simon told that he probably is roughly the same as Melrose, but if he had to put money, he probably would put it on it being true. And I tried to actually, I asked Dima for, I have been asking Dima for quite a long time to give me his opinion. And finally, yesterday, he told that if he were to put money, he again thinks it's rather true than false. But yeah, actually, I probably will be opening a book after the lecture, so if you want to make a small bet, then come to me. Right, so up to now, so I will be talking about periodic and almost periodic situations, but before these conjectures surprisingly were known only for potentials with compact support, and this is Popov, Shubin, and Weinberg. And actually, in the proof, they were using the wave equation method that was mentioned a little bit earlier today. So essentially, they have constructed the solutions of wave equation, but the thing is that if potential has compact support, then after a while, after your solution sort of goes out of the support of potential, they can construct whatever is going on afterwards explicitly, because I mean, you know explicit solutions of wave equation in RD, so as soon as you move out of the support of potential, you can, and that allows you actually to get back from, so once you have constructed this wave equation, then you apply the inverse Fourier transform instead of using the Tauberian theorems that are standard in these techniques, and then this allows you to compute the complete asymptotics of integrated density of states. Right, yeah, so they were using the wave equation method. Now, as Fritz has mentioned, it looks like even in one-dimensional situation, nobody knows what the answer is, and I think this is really quite embarrassing situation, because I mean this should be, I mean, something we in one-dimensional case probably should be able to answer. But of course the problem is that whenever we can say something definite, it means that we have some structure at infinity. And probably if the conjecture fails, then it fails because we have no structure at infinity. But when we have no structure at infinity, then it's very difficult basically to tell what the local density of state is, what spectral projection is, because I mean we don't know anything about spectrum of this operator. Right. Okay. So now actual results. So we will restrict ourselves to very, very special subclass of USB potentials. So potentials will be either periodic. So in general, we have our results for almost periodic potentials. But for simplicity, I will restrict in this talk, I will restrict myself to the case of periodic or quasi-periodic. The thing is that almost periodic potentials, I will need the whole screen of technical conditions in order to formulate theorems. So if potential satisfies a bunch of conditions, then the results hold, and they're a bit too technical to formulate. Right? What do I mean by quasi-periodic? So by quasi-periodic, I mean something different than probably most people in this room mean by quasi-periodic. And by quasi-periodic, I mean simply the finite linear combination of exponentials. Sorry? Standard. I thought it's finite torus, what many people mean by... No? Okay. Well, that's good news. Anyway, so this is what I mean by quasi-periodic. Yeah, so as I said, we can also extend results to almost periodic case, but it's too technical. Now, of course, in this situation, when our potential is either periodic or almost periodic, we have very important object. That is the integrated density of states. Well, okay, I will not define this object. It was defined already during the instructional school, which we have at the beginning of this program. And by the way, I assume that everybody here knows all the material that was discussed in the instructional school, so I will not really explain, or maybe, okay, maybe I will just remind you that integrated density of states, so there is standard definition, that is box definition, and it is the following. You take your operator, you restrict it to large box, you put some Dirichlet conditions on sides of the box, say Dirichlet, then when you restrict your operator to this box, you will get operator with discrete spectrum, you count how many eigenvalues you have below some point lambda, divide by volume of the box, let size of the box go to infinity, and this is the object you have in the left. So this is your integrated density of states. And I think several people have already introduced this object at this workshop. Right, now, and then it turns out that in our setting, when we integrate the local density of states, or rather take its mean, special mean, so then the result will exist, so the limit in the right will exist, and it will be the integrated density of states. I must also say that what I have just explained, the box definition of integrated density of states, is very nice definition. It's definition, I guess, that physicists use. Unfortunately, it will not be very convenient for us, because at some stage in my talk, our operators will stop being differential and will start being pseudo-differential. So as Alex Sobolev explained in his course in the school, I mean, we do this not because we want to generalize our results as much as we can, but because just it is in the nature of the method that at some stage we have to work with pseudo-differential operators. And for pseudo-differential operators, of course, the box definition doesn't make much sense, because, I mean, boundary value problems for pseudo-differential operators is a tricky business. I want to avoid it. So for me, actually, this formula is the definition of integrated density of states. Right, and also, so this formula is called Pastur-Shubin. I think many people have proved it independently. I think Avram Simon have proved it independently, and I think Pastur was the first person who actually has proved it. Right, now, so let's just recall what our conjecture says. Our conjecture says that we have complete asymptotic expansion, so that our local density of states admits complete asymptotic expansion up to all the way up to infinity. Now, suppose that we prove this asymptotic expansion, and suppose that moreover all the coefficients and, well, the entire asymptotic expansion is uniform in x, in special variable. Then we can integrate both sides, or take rather mean of both sides, and then it means that if we know complete asymptotic expansion for local density of states, we automatically have complete asymptotic expansion for the integrated density of states, right? So obtaining complete asymptotic expansion for integrated density of states is actually a weaker statement than for local density of states, right? And this subject, I mean, studying the asymptotic behavior of integrated density of states for large energies, I mean, it's something that has been, many people have studied in this context of periodic, or, well, especially periodic, actually, potentials. And this is the brief history of the subject. So again, I am repeating what Fritz has already said. So complete asymptotic expansion in one-dimensional case was obtained by Schenk-Shubin. Now, in two-dimensional case, Alex Sobolev has obtained a formula with 3 asymptotic terms. So maybe let me remind you that 3 formula number 3 is infinitely many asymptotic terms, and formula 4 is k plus 1 asymptotic terms. So when we say that Alex has obtained formula with k equals 2, it means 3 asymptotic terms, and this is the remainder estimate that he has obtained. Then in dimensions higher than 3, many people were working on this, and several people sit in this room. And I think the best remainder estimate was due to Yulia Karpeshina. So, and it's slightly better in 3-dimensional case, and it's this power of lambda, so slightly worse in dimensions higher than 3. Right, and in almost periodic case, one-dimensional situation was completely studied by Savin, so he has obtained complete asymptotic expansion of density of states. In higher dimensional cases, situations, dimension 2 or higher, only first asymptotic terms was known due to Shubin. And we with Roman, we started working on this problem, assuming that potential is periodic. And when we proved something, it was actually quite surprising to us when we realized that almost entire proof that we have obtained in periodic case could be extended for quasi-periodic and almost periodic situation. And so we have obtained the infinite asymptotic expansion in all dimensions first of all, for smooth periodic potentials. And for quasi-periodic potentials, we also have obtained this asymptotic expansion under one additional assumption. And additional assumption is slightly non-standard when we talk about what people usually assume for quasi-periodic, almost periodic situation. In the sense that this assumption is not Diophantine condition, it is something else. So what is this? So first of all, for any set S, we can denote by Z of S collection of all linear combinations, finite linear combination of elements of S with integer coefficients. So even if S is finite set, Z of S could be quite complicated. It could be a dense set in RD, but it is countable set. Right, and now our condition that we assume for in the quasi-periodic case is that if we have D vectors, D frequencies, so I call this set capital theta the set of frequencies. Suppose I have D frequencies, then whatever set they generate is discrete. Which means, I mean, maybe this is slightly not very convenient formulation. So another reformulation is like this: if we have D vectors from this complicated set, then these vectors are either linearly independent, or if they're linearly independent, they're linearly independent with rational coefficients. With rational or integer coefficients. Well, what this condition actually means in small dimensions. So in 1D case, this condition is trivially satisfied. In 2-dimensional case, this condition means that if we have two collinear vectors that have precisely the same direction, then their lengths are, one is rational multiple of each other, of the other. So their lengths are commensurate. In higher dimensions, again, it means, so in dimension 3, it means that if we have 3 vectors that belong to the same plane, then these vectors must satisfy some extra conditions. So we do not care if 2 vectors are not collinear, but the angle is very small. We do not care how small the angle is. So this is slightly different spirit to Diophantine type conditions that people often assume. And I must also say that this condition is obviously generic, because at each step, when we choose each frequency, we have to throw away countably many hyperplanes. So, I mean, this condition is obviously generic in measure theoretical and probabilistic sense. And then we have proved the theorem that for quasi-periodic potential satisfying this condition, we also have complete asymptotic expansion of integrated density of states. So what about the local density of states or the asymptotic behavior of spectral function of the diagonal? So actually not much really has been known. So in one-dimensional periodic case, again, Shubin-Schenk have proved complete asymptotic expansion of both local density of states and the spectral function. Otherwise, only one-term asymptotics on the diagonal and just upper and lower bounds of the diagonal, as far as I know, have been known. Right, and now actually the main result of the talk. So suppose that our potential satisfies the same conditions which we have formulated, so either smooth periodic or quasi-periodic satisfying this strange condition, then first of all, on the diagonal, our spectral function admits complete asymptotic expansion, and of the diagonal we also have complete asymptotic expansion, and essentially this expansion is in the spirit what you probably expect it should be. I mean, if you think of the unperturbed situation of pure Laplacian, think of its asymptotic expansion of its spectral function, and then this asymptotic expansion looks really precisely like the asymptotic expansion in the unperturbed case. So not much surprises in the formulation of the result, but I mean, I would say that most surprising for us was that the methods that we use are actually good enough in order to obtain complete asymptotic expansion. Yeah? Different, yes, yeah. I mean, this accent was because first we roll this asymptotic with e to the plus and e to the minus, I mean, two exponentials, yeah, but... A joke, it was a crazy. Yeah. Right, but the asymptotic for spectral function of the diagonal, we can obtain not for all collections of x's and y, but only assuming that x minus y is generic direction. And essentially, what do I mean by generic direction? If you remember the set theta of the potentials, so we construct the set z of theta, so all linear combinations of frequencies with integer coefficients. And our genericity assumption is that x minus y is not orthogonal to anything that is present in the set z of theta.
The expansions, do they match in any sense? Then, you know?
No, because I will tell you in a second. I will tell you something about uniformity. So, and they are not they are not so uniform, so you can match them. Okay, so before talking about uniformity, so couple of comments about this result. So first of all, what we really prove on the diagonal is actually much more scary looking asymptotic expansion. So it has, first of all, it has some logarithmic terms present, and also it has more powers of lambda. So here powers of lambda go with step 1/2, with half integer steps, whereas in actual asymptotic formula, powers of lambda go with step 1. So what we actually do, we prove this asymptotic expansion, and then we use the magical results by people who studied the heat asymptotics of heat kernel, so Hitrif, Kalturovich, Karateyev, Pushnitsky, who basically tell us that a lot of terms in this infinite expansion are actually zeros. So in particular, all logarithms disappear, and half of the powers of lambda also disappear. So they just seem to be here, but it is a mirage. And I must actually say that the fact that they disappear is a little bit, I would say some magic is going on here. Because the way we compute this asymptotic expansion, we compute it by computing some complicated integrals along different areas of the dual space, so where variable psi lies. So we compute some complicated volumes of some objects. We cut dual space into different parts, complicated volumes of various objects coming from different parts of dual space. And if you look locally, so if you look at just some proportion, some part of dual space, then all these extra terms are actually present there. So all the logarithms, all powers of lambda are locally present when we compute these contributions. But then we just know that when we sum them up over entire dual space, then quite a few of them magically cancel each out. So, and this cancellation does not happen, as far as we know, for if we initially studied the asymptotic behavior of pseudo-differential operators. So not Laplacian, but if we want to study pseudo-differential operators, then we think that logarithms are actually there. And in fact, there is a result joined with Sergei Morozov, Roman Sterebnik, and myself, when we studied the asymptotic behavior of integrated density of states for pseudo-differential operators. And actually, logarithms are there. So logarithms are by nature there, but they just disappear because our operator is differential.
Is the logarithm or also powers of
logarithm? I think powers also appear. Yeah, I haven't checked it because I mean it's really quite involved calculations, but I think powers also are actually there. Right. So good news is that when we want to study asymptotic on the diagonal, then somebody told us already what the coefficients are, and we can throw away quite a few extra terms. Unfortunately, when we want to study asymptotic expansion of the diagonal, then nobody knows what the coefficients are. So there are no good results about heat kernel asymptotics, and so these coefficients are just some numbers, or rather some functions of x and y. We do not know what these numbers are. And it might well be that some of them turn out to be zeros. We do not know. Now, concerning Valeri's question, so uniformity. So the first asymptotics is uniform in x. Second asymptotic expansion, first of all, if you fix the direction of x minus y, this asymptotic is uniform when distance between x and y is bounded away from 0 and infinity. So you cannot really make x go towards y because, I mean, there is no uniformity here. Now, if you want to change direction of x minus y, then it's a bit tricky, and in general there is no uniformity when you want to change direction of x minus y, because this generic set, where x set of directions, it is actually has no open components, so you cannot really change direction easily. On the other hand, if you are not interested in infinitely many terms, but if you want to study only first 5 terms, for first finitely many terms, then actually the asymptotic becomes uniform so you can change direction a little bit, and the asymptotic will be uniform in this.
So x minus y in modulus is bounded below by lambda and some power, right?
By constant. So, but I mean, if you want to check what happens if x goes to 0 as lambda to some negative power, I mean, it's possible, but we haven't studied this. But I think this is what natural assumption would be, yeah.
And the upper asymptotics, it is valid on the diagonal and no chance to extend it in a tiny neighborhood of the diagonal.
No. We were quite happy to get these results, I mean, the way they are, I think. But it's of course interesting question to check how one asymptotics turns into the other one. Yeah, but this is completely different question. And we suspect actually even probably easier question is the following. So we think that for arbitrary x minus y, we would have the same asymptotic, so even in this resonance direction. But we try to actually check how one asymptotics, I mean when x minus y is not orthogonal and you change direction a little bit, how one asymptotics turns into the other one. And this is very difficult. Right, Okay, so some words about the method. So despite the fact that I am a student of Boris Moiseyevich Levitan, I was not using the method of wave equation. I was using a different method, so the method of gauge transform, which was developed by Alex Sobolev, and Alex Sobolev gave a very nice talk, series of lectures during the instructional conference when he explained what the gauge transform is. So, and as I said, I am assuming that everybody has listened to these lectures. So I will just remind you what the gauge transform method actually does. So it constructs, in a sense, it's maybe somehow philosophically similar to other method, wave equation method, or I don't know, heat equation method, in a sense that instead of studying what happens for our operator and the spectral properties of our operator, we study some properties of some other object. In our case, this object is a gauge transformed operator. And what is this gauge transform operator? So we construct two operators, H1 and H2, such that first of all, the first operator is unitary equivalent to the operator H. Second operator is diagonal, or this, to rephrase this, it has constant coefficients. Now, this would be our ultimate goal, to make second operator have constant coefficients. Unfortunately, we do not quite can make it have constant coefficients, and our enemy here is small denominators, as it is pretty often happens in KAM method. So this, by the way, this gauge transform is probably should be looked at as some variation of KAM approach. So whenever we have small denominators, we do nothing. We keep these terms unchanged. So as a result, our operator H2 is almost diagonal, meaning for some large proportion of values of dual variable xi, the operator is diagonal, but there are some regions in which this operator H2 is not diagonal. Right, and what is relationship between H1 and H2? They are close to each other. Now, here I have to be careful. So what do I mean by close? By the way, first of all, we do this gauge transform in some region of spectral parameters. So we fix value of lambda and make this gauge transform for values of dual variables that have length close to lambda. Now, what do I mean by close? So the normal thing that was until now was good for us, very good for us, is that norm of the difference is smaller than lambda to some power minus n. So where n is as large as we want, say minus a million. So in this,
if you
yes,
say symbol, do you mean principal symbol or do you mean the whole symbol of the operator?
I mean the whole symbol. Yeah, well, principal symbol is, is mod xi squared, so it has, yeah, but entire symbol disappears. Right, and I haven't emphasized this, but I have written it. So operators H1 and H2 are no longer differential; they're pseudo-differential. So this is why we need to learn how to work with pseudo-differential periodic and almost periodic operators. Right. So the one way to measure smallness of the difference is to say that norm of the difference is small. But unfortunately, this is not. This was not good enough for our purposes when we were working on this problem. And what we need is a little bit more. So even if you take the difference and multiply it by actually as is positive here, so multiply them by some fixed power of Laplacian, then still even the norm of this object will be small. Right, and I must say that this smallness is still possible to achieve using the gauge transform method. Right, now after we have performed this gauge transform and we have found these two operators H1 and H2, and I will not tell you how to find these operators because Alex Sobolev has taught entire mini course about construction of such operators. we need to do two things. So first of all, we have simplified our operator. So we have reduced our operator to something that is almost constant coefficients. So we have to study this operator that has almost constant coefficients. And we have to compute either integrated density of states or local density of states or whichever other things we are trying to compute for this particular operator. And this is actually, this part of the job is where the main difficulty lies. So so our operator is almost diagonal. So first of all, it is not quite diagonal. So we still have some resonant areas where we have not diagonalized the operator. We have killed some matrix elements, some off-diagonal matrix elements, but not all of them. So we still have to study what happens in resonant areas because they do contribute to density of states. And actually, this is where you need really to think. So there are some methods. Actually, we applied some methods from functions of complex variables. So we actually had to go to complex plane in order to compute some objects. But this is where we have to think. But there are also additional difficulties, and they are the following. Suppose we even forget about resonant areas. Suppose that H2 has truly constant coefficient. So it is just diagonal operator. So then you want to compute the local density of states or integrated density of states. They are the same, in fact, for operators with constant coefficients. So how do we do it? Well, operator has constant coefficients, so it means that on the level of Fourier transform, it's just operator of multiplication by a function, right? And in order to compute the, say, integrated density of states, you just look at the set of points where the value of function is smaller than lambda, and you need to compute the volume of this point, or the volume of this set, right? So piece of cake. Unfortunately, it turns out to be very, very technically difficult task, because this actually domain, I mean, despite the fact that this domain is given by some explicit inequalities, the integral you obtain at the end when you try to compute its volume is very, very, very complicated. And by the way, when you compute this integral is where all these logarithms actually are coming into. And it's, the integrals are very scary to even to look at, so I will not show them to you, but they are quite difficult. And so this is where the major chunk of our work was. But what I want rather to discuss is, suppose you have performed this work. Suppose you have obtained everything you wanted to know about the operator H2. Now you want to get back to operator H, and now you want to prove that whichever objects you obtained, you have computed for operator H2 are close to corresponding objects of operator H, right? So, and the strategy of what we are doing is actually different when we were studying the asymptotic expansion of integrated density of states and of spectral function. So first of all, what was going on when we were studying the integrated density of states? So remember, we have three operators. So H, our initial operator, H1 that is unitarily equivalent to H, and H2 that is close to H1. Now, and we want to prove that once we have computed the integrated density of states for operator H2, it is close to integrated density of states of operator H. Now, then we need to answer two questions in order to make this deduction. So first of all, we want to find out whether it is true that the integrated density of states of operator H and of unitarily equivalent to it operator are the same. So this is the first big question. Second question is it true that integrated density of states of two operators that are close to each other, that the difference of integrated density of states is small? Now, it turns out that none of these questions is obvious or straightforward. And for example, the first question, the answer to the first question is in fact no in general. So if our operator H1, the only thing we know about operator H1 is that it is unitarily equivalent to operator H, in general, it doesn't follow that two integrated density of states are the same. In general, it wouldn't even follow that H1 has integrated density of states. Right? But what saves us is the knowledge of the fact that not they're just unitarily equivalent, but also we know that the operator U that provides unitary equivalence is also operator with almost periodic coefficient. So it belongs to a certain algebra. Yes?
Curious. Okay, matrices are of no interest for you because you work with a scalar problem, of course.
Yeah.
Okay. Question.
But well, I mean, right now we are trying to do gauge transform for matrix-valued problems.
If you were a matrix depending on X only, the integrated density of state will stay the same, obviously.
Matrix depending on X?
On X.
Not necessarily. It has to depend on X in periodic, almost periodic way. But it's, so your problem is when U is, or even scalar thing, when U is, say, 0 for, or let's say, okay, let's talk a little bit, but when U, for example, doesn't change on some interval of X, then it changes and becomes, say, 1 on much higher chunk of X. Then it becomes again 0 on even a larger chunk of X. Then even density of states might not exist, in fact.
So you are worried about the integrate.
I'm worrying about, yeah. So it essentially it should not really reshuffle your space too much. Okay. So and in order to answer both of these questions, the definition of integrated density of states that I have already given you, unfortunately, is not good enough. So we need another definition of integrated density of states. And so this is definition / theorem. And I will cheat a little bit because I will not tell you what this operator H tilde is. So operator, I will just do some hand waving. So operator H tilde is somehow our operator that is either periodic, almost periodic, extending to the hull of the frequencies. So essentially, roughly speaking, you just introduce some artificial variable to extend our initial operator that depended on X as an operator that depends on two variables, X and Y. And then the reason why we do this, because after introducing this fake variable, our new operator, H tilde, will belong to a nice operator algebra, von Neumann algebra, that is called a factor. Now, a factor is, roughly speaking, is an operator algebra that does not have too many commuting operators. And in these operators, we can define nice objects, like, for example, the relative of von Neumann dimension. So what is it? So let's just think naively. Our integrated density of states is somehow an analog of counting function, spectral counting function. And spectral counting function is just the trace of spectral projection, or the dimension of the range of spectral projection, right? Let's try to do the same in our situation. So let's just take spectral projection and take its trace. Obviously, the usual trace will be infinite, but there will be a nice way of regularizing this trace, and this is precisely the von Neumann trace in this factor I have talked a little bit about. And what is very nice about this trace is that this is honest trace. By honest trace, I mean trace of AB equals trace of BA, assuming that A and B belong to the same factor. So therefore, I can basically shift U minus 1 from first argument to the end and cancel it with U, assuming that U is actually an element from our von Neumann algebra. So this is what we do with problem 1. What we do with problem 2? So problem 2, remember, it was that if we have two operators that are close to each other, then densities of states are also close to each other. Right now, if we knew in advance that the integrated density of states is monotone with respect to the operator, well, what does it mean? It means that if you increase the operator, you decrease the density of states. Now, this property is obviously satisfied if we, say, talk about the box definition of density of states, because, I mean, if we take restriction of operator to a box, we increase the operator, the restriction would be increased, so the counting function would go down, so we would have monotonicity. Right, and as soon as we have monotonicity, it would mean that from the fact that norm of difference of two operators is small, it would follow that one operator can be sandwiched between two expressions like this, and then it would imply also that the density of states of one operator is sandwiched between integrated density of states of the other operator, and the price we have to pay is just some small shift in the spectral variable. And I mean, if we know, that would mean that if we know complete asymptotic expansion of integrated density of states of second operator, we immediately would get the same expansion for the first operator. Unfortunately, the problem is that that our box definition of density of states only holds for differential operators. For pseudo-differential operators, it doesn't hold. So we have, for pseudo-differential operators, we have to use either the Pastur-Shubin formula. Unfortunately, I do not know how to deduce monotonicity from Pastur-Shubin formula. So we have to use, again, C-star algebra approach. And if you play around with this C-star algebraic approach, you can define your integrated density of states in a variational way, and then from this variational definition, it would immediately follow the monotonicity. So this is what we do for integrated density of states, right? So we have to use the C-star algebraic approach. Now, what we do in case of spectral function, so the kernel of spectral projection. So first of all, we do probably very obvious thing for the discrete group of people studying discrete Schrödinger operator, and maybe not very natural thing for people who do the continuous Schrödinger operator. So what we do, we just say that my spectral function I can construct in very simple way. I take spectral projection, I apply it to one delta function, and I take in a product with the other delta function. Right? So as I said, for discrete Schrödinger operators, it's not really a big deal because deltas then belong to L2. But our problem is that in our case, deltas are not elements in L2. But if we just forget for the second that there are some maybe problems with what we mean precisely by these inner products, and just think about this equation formally, then the first step, once we have this formula, is very easy. So when now we take H1 to be unitarily equivalent operator to H, then we just have the same right-hand side, only instead of delta, we have U applied to delta. Right? So how we deal with the problem that delta function is not an element in L2? Well, we just notice that despite the fact that delta itself is not an element of L2, but when we take delta and apply spectral projection, then we immediately would get an element of L2, and of course we can, when we write this inner product, we can move this spectral projection to the right, so it will be nice inner product between two functions, both are elements of L2. Now, why the spectral projection applied to delta function is an element of L2? Well, this is, I would say, very straightforward. So there is a lemma, so take delta function, apply spectral projection, then L2 norm, well, first of all, will be finite, and moreover, it will be growing as lambda to some power. And the proof is actually, well, I thought I should show you at least a proof of at least one statement. So the proof is, as you can see, just 2 lines. So you just compute what is the L2 norm of this object. So this is just integral of spectral function along in y variables, and you notice that spectral function is first of all real valued, secondly symmetric, so you can write it like this, and then you just see that what we have here is just the integral kernel of the operator E times E, so E squared, E is projection, so we just get integral kernel of E. And the last thing that the spectral function grows as lambda to power d over 2 is just standard fact from spectral asymptotics. I think Agman was the first person who proved it. Right, now we have, I still have 3 minutes, so I can very quickly go along the second problem. So second problem is like this. So we know the difference of two operators is small. Can we say something about the difference of spectral projections? Well, in general, no. Because, I mean, for example, what could happen, one operator has eigenvalue, for example, just below lambda, you add something very small, eigenvalue moves and becomes slightly above lambda, and spectral projection has changed tremendously. So we cannot really say that norm of difference of spectral projections is small, but we can say that these spectral projections are close in certain strong sense. So what do I mean by this? Well, first of all, I will denote by, when lambda is subset of R, I denote by E of lambda h the spectral projection on this set lambda. So lambda is Borel set. And then it turns out that the following statement holds. I mean, we haven't really seen this statement anywhere, so we had to prove it. Suppose two operators are close. Then whenever we have f is arbitrary vector, and delta is any number larger than epsilon, and later we will take delta to be square root of epsilon, then we can estimate the norm of the vector that we will obtain when we apply the difference of spectral projections to f. So the first element will be a spectral projection onto the interval of very small length. So we hope that if we take f that doesn't have huge proportion of its support in this interval, then this norm of the first object is going to be small. And by the way, for f, we will take a delta function, so it will be something that we will be able sort of to compute and to check that this object is small. Second term is small because epsilon times delta minus 1 is small. So epsilon is very small, delta is also small, but not as small as epsilon. So the second term is small because of this term epsilon delta minus 1. And even if we take f delta function, the norm of this object is still finite, so the second term is small. However, the third term, despite the fact that it has small coefficient in front of it, epsilon delta minus 1, it has norm of f, and so if we take f delta function, this estimate is not good enough for us. And by the way, it looks like 2 pi surprisingly appearing here. It might be actually the optimal coefficient here. But still, this lemma is not quite good enough because we have this nasty last term. So, and we want to take f to be delta function. So we need to improve it a little bit. So just the last slide. So suppose that we know the result that I have advertised a little bit earlier. So the difference of the operators is small even after we multiply them by Laplace to some power. Then we have the same estimate, only the last bit, instead of having norm of f, we have norm of, think of h2 as Laplacian, so Laplacian to power minus s applied to f. So as soon as s is larger than d over 2, we have this object being in L2, so the last term also would have small norm, and everything will work. And I think this is good time for me to stop.
Any questions?
Yes?
So it's not directly related to what you said. When I was looking at this kind of problem, there was the question of looking at the case with magnetic potential, periodic potential. Are there any progress in this direction?
Well, if we talk about integrated density of states, yeah, we have obtained complete asymptotics, so jointly with Sergei and Roman. If we look at local density of states, the answer is no, but probably not yet. I mean, I guess this method probably could be extended to magnetic case.
Other questions? So in the last thing about projections, if you replace it by smooth cutoff functions, the next short answer becomes yes, and the error will be of the order of the previous.
Yes, but smooth cutoffs are not good. I mean, the whole point is that the spectral projection is, I mean, the whole, I mean, source of the difficulties is that spectral projection is not smooth cutoff, it is very rough cutoff. Yeah?
What goes wrong if your condition on the set theta or z theta is satisfied? Because it's somehow I think you believe it's true. Also
You mean conjunction condition A is not satisfied? So this is your question. What happens when condition A is not satisfied? This is right.
I believe it's true anyway, right? Without this condition.
We believe it is true, and we even thought for a while that we could prove it using some operator algebraic approach. I mean, unfortunately, the thing is that, okay, so how we use this condition? So we, instead of looking at our operator, we sort of look at collection of operators of smaller dimension. And this condition guarantees that these operators acting on smaller dimensions are already periodic. They are not almost periodic or quasi-periodic, they are honest to God periodic. And then for these operators, then we could, okay, we could do some techniques, and in particular, something becomes finite dimensional, and we could work with counting function of eigenvalues of this finite dimensional object. If we don't have this condition, then this something becomes infinite dimensional. And we thought that we could, by using the same sort of definition of replacing counting function by these traces of von Neumann, irregularized von Neumann traces, we could then mimic our approach here and extend it to cases when condition A is not satisfied. It might be that we do not know operator algebras good enough in order to perform it, but I mean, we were stuck at some stage, and I mean, if we have somebody who is good in operator algebras and wants to discuss this, I mean, we would be happy to look at it. But I mean, we just couldn't do it on our own.
Other questions? Okay, so let's thank the speaker again.